they represent is essentially irrelevant. In essence, you have learned a rule. I can eat the green fruit, I can eat the red fruit. And that's fine up to a point. But when the problems become more complex later in the course, or perhaps in a more advanced course, should you continue past high school chemistry, you can't always use the factor label. When you get to equilibrium problems, you can't just use factor label. And if you haven't understood that equilibrium problem becomes the orange fruit, and you don't know what to do. So you've got to develop understanding. You've got to avoid trying to use these gimmicks. So what am I recommending? Here's what I'm recommending to you. If you are a student that understands concepts quickly and easily, for example, when we talk about density or the mole or molarity or mass or volume or energy, if these kinds of things make sense to you right off the bat, and if quantities expressed as a this per that, like grams per cubic centimeter or grams per mole or moles per liter or liters per mole, if things like this make sense to you, if you can visualize them easily in your mind, then don't ever use factor label, don't ever use proportions, don't ever use formulas. It's not necessary. But if you're like most students, like the majority of students, things like this are not immediately obvious. Now that kind of puts you in a box because you want to survive. So when you hit a little wall, when you're not sure what, for example, grams per mole is really all about, you say, how can I survive? You say, show me a way, show me a proportion method, show me a formula, show me a factor label method so I can get through today. And that's fine. But what about tomorrow? You've got to work on understanding. So let me say this. When you are presented with a problem in this series of lectures, here is what you should do. Actually, this is probably what you must do. If you're not willing to do this, you're not going to benefit from these lectures in this approach. Try to understand, visualize, put quantities together in a natural, logical way. Take time to try and really understand what the numbers in the problem are really representing. Some will be amounts, some will be what we have called this per that's. In the students in rooms problem, you would close your eyes and you would see a school with 3,000 students. And you would see a little room with 30 students in it. And you would sit and you would think and you would visualize. And you would realize, oh, this was one of those Gazinta problems. I have to see how many times 30 goes into 3,000. You would put these quantities together in the absolute natural way that they have to go together. To put them together in any other way wouldn't make any sense. After you do this, if you want to check your answer, then check it by proportions or check it by factor label or a formula or whatever approach you may have used in the past. But when you check it, don't just check it mechanically. Think about what you're really doing when you set up these factors. What's really going on in that problem? Let's consider the students and rooms problem again, which I said really illustrates most of the quantitative reasoning that you have to do in a high school chemistry class. Even though no student of mine has ever set up this problem incorrectly, for the purposes of discussion, I would argue that there are really only three things that any student might do with these numbers. You might divide the 3,000 by the 30. You might divide the 30 by the 3,000, or you might multiply the numbers 3,000 times 30. When I teach my students, I like to pretend that I don't understand how to work this problem, that I did this, that I reasoned this way. Okay, there's 3,000 students in a high school. There's 30 students per room. How many rooms? 100th. That's it, 0.01 rooms. Oddly enough, when I say that I got 1/100th of a room for my answer, the students will literally laugh. And I find that very interesting. Why would you laugh at something like this? I've often thought that, maybe I should go to Las Vegas and work as a warm-up act for some headliner's show. I could be the first quantitative comedian. I could run out on stage and say, okay, guys, 3,000 students in a high school, 30 students per room. How many rooms? 1/100th. The audience would roar and they could, pay me $100,000 a week or something. Why do students literally laugh at this? I think I know why. Students of humor tell us that one aspect of some types of humor relates to what is called an incongruity. Things are put together that shouldn't be together. And for whatever reason, human beings typically find this to be funny. This is so obviously outrageously wrong. It can't possibly be true. And most students can actually explain why this doesn't make any sense. If I say to them, why isn't the answer 1/100th of a room? They will say something like this. Look, if there are 30 students in one room, there would be 30 students inside that room. Then how could a tiny fraction of a room, 1/100th of a room, possibly have 3,000 students in it? That just doesn't make any sense. That's simple to see, completely obvious to everyone. So then I'll say, yeah, you're right. That clearly wasn't the way to work the problem. What you really need to do is multiply the numbers. 3,000 students, 30 students per room. Clearly, there are 90,000 rooms in the school. Of course, the students immediately see that this doesn't make any sense either, and they can't explain it. If you had 90,000 rooms, I don't think we'll put them all on the graphic. If I put only one student in each room, I would already have 90,000 students. How could I possibly put 30 students in each room and end up with only a total of 3,000 students? That just doesn't make any sense. And this is what I'm trying to point out to you. Most of the problems that you are going to be asked to solve in high school chemistry are going to involve applying logic exactly identical. Not similar, not kind of like, but exactly identical to the logic that you applied so naturally in this kind of a problem. Then why does it sometimes seem so difficult to apply the simple and natural logic to chemistry problems? Well, we touched on this in the first lecture. First, there's two reasons. First, the numbers usually aren't nice. Chemistry typically doesn't have 3,030. Chemistry has numbers like 28.6 grams with decimals. And chemistry uses exponential numbers like 6.02 times 10 to the 23rd. And that's more difficult to reason with. But we've got calculators. And calculators have in fact removed much of this difficulty. In fact, we're going to work very hard on getting you to ignore the specific numbers given in the problem, and instead focus your attention on the concepts, because the concept is the same, whether there are 3,000 students or 2,716 students. It doesn't make any difference. The real reason, the major reason students sometimes find chemistry problems difficult is because of one central problem. They really don't understand what the numbers truly represent. Very often in a chemistry class, when you're working on something like the mole, you'll present the class with a problem, and the problem might be something like, you have 7.28 grams of something, and it weighs 58.5 grams per mole. And then you ask a student, how many moles of the substance do you have? And some students have trouble with that. The correct way to work this particular problem, not that we have to understand this right now, is to take the 7.28 grams and then divide it by the 58.5 grams per mole. But a lot of students won't do that. They will take the 58.5 and divide it by the 7.28. Or they'll take the two numbers and they'll multiply them. I get very upset at times when I see other students laugh at them. I will ask, why are you laughing at them? They say something like, well, that's really silly. And you know something? Actually, it's silly. But it's only silly if you understand what these quantities represent. To a student who understands what a gram really is, I don't mean rattle off some definition from memory, I mean really understand what a gram represents, the 7.28 grams is just like 3,000 students to him or her. And if you really understand what is meant by 58.5 grams per mole, then this is just like 30 students per room. And then this problem becomes just as easy as the students in rooms problem. And therefore, students who understand this will often laugh at the students that don't understand it. That, as I said, gets me very upset. They'll say things like, oh, how could you possibly work the problem by multiplying the number? That's really stupid. Well, you know something? That's not stupid at all. If you don't understand what the numbers mean, then putting them together in one way makes just as much sense as putting them together in a different way. I tell my students who are laughing, I will give you $1 million and an A in this class if you can tell me the answer to this problem. And I could make you the same offer. There's no way to win. The numbers are 5.26 and 3.15. Okay, what's the answer? They'll say, well, do I multiply, divide, add, subtract? If I divide, which number do I put on top? I don't know what to do. You didn't tell me what the numbers represent. Of course. And that's why I can offer you $1 million. If you don't know what the numbers mean, if the numbers don't have any meaning, then any mathematical operation is just as sensible, just as logical as any other mathematical operation. But when you do understand what the numbers mean, then you see that there is only one simple, natural, logical way to put these numbers together. And that really is our ultimate goal. To have you understand what is meant by grams and moles and liters and molecules and grams per mole and grams per cubic centimeter and moles per liter and liters per mole, all of which probably sounds very confusing at this point. But when you truly understand what is meant by all of that, the whole chemistry course literally becomes just as easy as the students and rooms problem. And that's what we're going to be striving for. I said earlier that incorporated into that students and rooms problem, as simple as it appears, is literally almost all the logical quantitative reasoning ideas that you need to know to succeed in high school chemistry. And I really meant it. All the problems we are going to work, okay, well, virtually all the problems. There's some exceptions like pH or some equilibrium calculations, involve exactly the same kind of reasoning. When you realize that, when you understand that, it is absolutely beautiful, because the entire chemistry course becomes not a series of completely unrelated problems, not a series of one rule after another and a new formula after some other formula after yet another formula, until it becomes a hodgepodge of apparently unrelated and confusing stuff. Instead, it becomes one magnificent edifice, tied together so beautifully and so logically. In the next lecture, we're going to take a closer look at the ideas that we've talked about in this lecture.